All right. Sorry for the technical difficulties. So yes, so we have four different applications that are at the very end of the chapter. I was saying when my battery died, you can approximate the probability, but if you just try to do it directly, what ends up happening is you're going to sample a whole lot of low probability regions, and it might take you in a high dimensional space, it might take you a jillion samples, and you're it's going to take you forever. You're not going to get a good estimate. So there's a technique called importance sampling. Not really going to cover the details, but basically you uh, you're weighting the samples that you do, um, and and so then you more rapidly will converge. Importance samplings used in reinforcement learning also. Um, so that's a technique you can use. I'm not aware if people actually do this because I don't think this is a terribly convenient way to estimate probability. But if you really needed to, you could. And anytime you have a likelihood, then if you're trying to do things like outlier detection, so if you did find something and it you could use this to say, wow, this was a particularly low value. I suspect this might be an outlier. So all the places where you look for outliers, like you know, security when you're looking for unusual network activity and things like that. Generation. We said that these four chapters are all generative models. If you look at the top two rows, so row A is a straight image from a vanilla VAE using spherical Gaussians. And then what you do is you add a little bit of random Gaussian noise to it, and you will get an image that looks, I think the one on the right looks the worst, but they look somewhat okay. They do tend to be blurry. Lots of generative models tend to be blurry, so you can fix that a little bit. But anyway, you can see row D are actual VAE images that were generated, much higher quality, but this required more complex architecture. So they used hierarchical priors. Not going to talk about what that technique is, partly because we don't have time, partly because I actually don't know hierarchical priors. Um, but you can see that this general technique you can build on. Okay. VAEs are used inside of other models in various places. And I have not read the next chapter yet, but the author talks about how diffusion models, even though they are not, I've not seen any other place where they're talked about as a complex form of VAE, but apparently Simon Prince says you can just think of them as a particularly complicated form of VAE. So that'll be interesting in the next chapter. With VAEs, because you have a latent space, you can do modifications in the latent space. And so here you have the original image on the left. She has her mouth closed and she's not smiling. If you averaged like 100 pictures of people not smiling and 100 pictures of people smiling, and you just said, what's the difference in direction in latent space between those two averages, then basically you can take that vector and you can add a little bit of it to the original image. You can add half of it to the original image, or you can add the full-blown thing. And that's basically the left to right direction of more and more smiling. You could do a similar thing with people's mouths closed, mouths open, and say, well, that's this direction. So I can add a little bit of it or a lot of it. And so moving around in latent space, you see this cool little grid of 15 different perturbations of our original image. In order to do this, in order to have meaningful directions in latent space, what we do want is this thing we talked about, the question that was asked. We actually want disentangled latent spaces. We want human interpretable directions that are completely independent, so that smile is just one direction. And when you move in that direction, it doesn't change the hair color, right? And you want open mouth where you move that and it doesn't change their ears when you move, right? So all kinds of generative models, people seek this out. And so there's a beta VAE model that I mentioned where you put higher weight on the KL divergence term, the second term. There's also a total correlation VAE where they added an extra loss term where they calculated the correlation between the different directions. And so basically you penalize it when they're highly correlated. And so then that basically enforces you can do whatever you want in sort of linear algebra, but I'm going to penalize you if these human readable coordinates have high correlation. And so then that basically encourages the model, forces the model to say, I'm going to do what I do, but when I do it, I'm going to do it all along this particular set of bases, because you're penalizing me when I don't use those bases, when I go across them, but I can do anything I want in the directions within. So within a given floating point number, I can do whatever movement I want around, and you're not going to penalize me. But as soon as you say floating point 1 and floating point 2 are correlated, you're going to penalize me. So you can see how this is very much going to encourage the model to, whatever math it comes up with, to align it to our human interpretable convenient basis. All right, so that's the 4 applications. And so now the final summary is we're learning a complicated latent variable model able to handle real-world multivariate high-dimensional problems. We're going to generate new examples we run the encoder neural network. We sample from that latent variable. We pass the sample through the decoder neural network, and we add a little bit of Gaussian noise. Once again, this differs from a simple autoencoder because in the middle of that, you have a single embedding, whereas here you have a distribution. You can't do generation unless you have a probability distribution that you're sampling from. And then finally, the maximum likelihood training of this VAE requires estimating the likelihood. So we use this lower bound. We're going to use variational approximation. We're going to estimate using samples, little Monte Carlo sampling. And when you combine all of those things, we have a computationally tractable technique. And it allows us to build the encoder, the decoder. Generally speaking, we throw away the encoder when we're done training. We just use the decoder. So this is the third of the 4 techniques. VAEs were in image generation were studied extensively, and you saw some of the higher quality images, but never quite made it to the summit. And so people were primarily using GANs. So if you've heard of like StyleGAN and some of the other GANs, primarily using those for the highest quality images. But there's a lot of things you couldn't do with GANs because GANs, you just sort of like, you get an image out, but you don't really, like here, it's not advisable, but you can kind of estimate the likelihood. With a GAN, you absolutely cannot do that at all. But unless you've been living on a rock, you've probably seen Stable Diffusion, DALL-E 3, some of these other models. And so lately now, our next chapter, diffusion models have really taken over the image generation space. And so we'll talk about those in the next chapter. In 1 week, we do have the monthly ML Papers event, so on June 1st. So chapter 18 will be in 2 weeks. It'll be on June 8th. Can use VAE and a GAN. Yeah, I don't know. I mean, obviously, I don't know every model that's out there. There's a model called VQVAE, which they use vector quantization, and that helps the image quality. And then there's an enhancement to that that's called VQGAN, but it's not really a GAN. Basically, what it is they just ran their VAE, and then they put a little discriminator at the end that says, I'm going to look at patches. So it's a patch GAN. We looked at the discriminator looks at little patches and says, do I think this patch looks realistic? I'm sure it's more complicated than that, but at the 10,000 foot level, basically, the patch discriminator says, does that look blurry? And if it looks blurry, it predicts it's a fake image. And if it looks very sharp and clear, it predicts that it's an authentic image. So basically, lots and lots and lots of places they've used now patch-GAN discriminators to just simply force models to have non-blurry images. And so what you get is very realistic images, but the realism is not necessarily authentic. So if you were like the expert and you knew that a certain type of fish has exactly this kind of scale pattern, and there's this relationship between every third scale must have this property, no, the GAN's not going to do that, because all it's doing is it's saying I'm generating something that at a low level seems very high resolution, seems very realistic, but it's not necessarily authentic. Okay. But most of the time when you're doing generation, you don't care about the high frequency stuff. So you have a picture of a cat and it's sitting outside in the grass. You really don't care which way the different blades of grass are pointing. You just care that the grass isn't blurry and that it looks like a real grass texture. So 99% of the time, this is a good thing and we don't care. But say, for example, like if you were trying to do like a protein molecule 3D way, this patch GAN is probably not going to help you, because it's just saying like, yeah, it's high res, but it doesn't mean that it's actually authentic to the physics of it or whatever. But again, for cat images, usually you just don't care about those kinds of things. All right. Any other questions before we wrap up?
I just had a quick question. Ted, thanks very much. It was really interesting, very nice presentation. I'm curious, I'm getting the feeling that maybe you could put any continuous function even in the middle. So roughly speaking, you can replace the Gaussian, like for example, these pins, these physics-inspired neural networks, or really anything, as long as you can make these lower bound arguments on the error, basically. Is that roughly true?
Yeah, so the question is about whether you could kind of, in the middle of the VAE, kind of put anything. I think I'm going to give my best attempt at an answer. I think what happens is you are going to run into some math problems if you don't pick super convenient things. So like there's this one place where we have this KL divergence. It's going to get a lot more expensive as soon as you pick anything else. And so, yes, I'm sure people have tried different things, but and you can look, there are entire books about variational inference.
Thank you.
But sorry for the background noise. But yes, the math gets very complicated as soon as you stray from your simplest distributions.
Yeah, thank you.
All right, one sec, guys.
Great, thanks.
Yeah.
There's a question in the room. Yeah.
And when it's overlapping, then correlation, and then could you please just explain how the intuition behind the correlation and overlapping parts of the picture?
I think I was talking about the total correlation VAE. Yeah. So one general concept is if you have data that you have represented by some embedding, okay, like this latent Z, okay, the linear algebra of it says it's a linear model, and so you move more in this direction and you're talking about darker colored hair, and you move more in this direction, you're talking about lighter colored hair, okay? And then a different direction represents longer fur versus shorter fur, and this direction represents the color of the eyes or whatever, okay? But the way linear algebra works is you have the origin, which is, your 0, 0 point, okay? And every direction from there, as far as linear algebra concerned, is equivalent. So when we write something three-dimensional, we write x, comma, y, comma, z. But in the world of linear algebra, if you were trying to model three things, like hair color, hair length, and eye color, there's no reason why they should slot into the x and the y and the z. It might just be something at a 30-degree angle this way, and something else might be at a 45-degree angle that way, and something else might be over here, okay? So essentially what it is just taking, you can think of something that's aligned to our notion of x, y, and z, and you can just rotate it, about the origin in any direction. And as far in terms of linear algebra, in terms of the way we build the neural networks, in terms of matrix multiply, it's completely equivalent. It's identical. So what you need to do is you need to teach the model somehow, I care about X, Y, and Z because it's convenient for me, because to you, you don't care. As a linear algebra matrix multiplier, you don't care about these different dimensions. But I need to somehow teach you that this is a principled basis that I care about. So then basically what happens is, imagine that you have hair length that is at a 45-degree angle between the X and the Y axis. That means then you're going to have correlation between your X and your Y. Okay? Because that's the direction of the hair. So anytime hair is longer, you're going to have a bigger X and a bigger Y. Now, not completely, because there's other things that'll affect, but you will still have pretty high correlation. And anytime you have shorter hair, then you'll have a smaller value on both. Okay? So if I calculate all these correlations and I penalize you whenever I find correlation, that means that if the model can find our bases and says, oh, okay, well then I'm just going to vary hair color only on the X direction. And I'm going to decide I'm only going to vary hair length on the Y direction. Now, it could have chosen Y instead of X or Z instead of X, but as long as it like picks each thing that it's varying along those, then we've basically taught it the principled basis that we like because it's convenient for us. And then now I can go create a web page and I can put sliders for X, Y, and Z. And you can see when I move this slider, the hair length changes, but nothing else changes. If I didn't do that, the sliders would still work, but you'd notice like, oh, every time the hair gets longer, the eyes also get darker. Every time the hair gets, whatever, darker, also the tail gets longer. And so it would still work. It's just not really what we want. We prefer them to be disentangled, so then we can just say, yep, I can just change the length of the tail and nothing else is really going to move. Yeah, thanks for the question. Yeah.
Could another way to do that, because it seems to me, like what you're saying, where you have these human features like hair length, that requires some manual data labeling to figure out, or unless I'm incorrect about that, right? It seems like you need, like if you want a parameter that corresponds to hair length, you have to like actually see, like train the model, to make sure that, across these generations, hair length isn't correlated across multiple variables, right? And to do that, you have to label some data, right?
So the question is about like labeling the data. So my understanding is most of the successful models, what you do is you find a way to encourage disentanglement, and then you don't have to label anything.
Okay, yeah. So I was
So,
thinking of like
yes.
dropout. Would that be one way to do that?
I don't think dropout would work. Again, it's just something that breaks the symmetry. In linear algebra, there's perfect symmetry where you can rotate in any direction. And if the model happens to be at this angle when it first learns this notion of eye color, there's no reason for it to move off of that. It's like, oh, this is working really well for me because, when it's further over this direction, it's lighter eyes, and further this direction is darker eyes. There's no reason for it to move off of it. So what you have to do is you have to give it some sort of external stimulus to say, I want to penalize you if you choose that, and I won't penalize you if you happen to choose something that's right along either the X or the Y axis. Okay. And so like StyleGAN was very successful. As far as I know, StyleGAN, there's an explicit concept of like coarse grain feature, medium, fine grain features. But amongst the different medium grain features, as far as I know, it's completely random. So you get this and you get like 10 features and you build your sliders. And then after you've built the sliders, you're like moving around, like, what's changing? Oh, it's the eye color. What changes when I move? It's not like the programmer was able to predetermine and say, I want this one to be eye color. They just know that it's a medium level feature, and you're like crossing your fingers that it'll pop out and it'll be what you want.
Yeah.
So yeah, so when you see things and they say that like this is the eyeglasses feature, they did not know in advance that that was going to be the eyeglasses feature. It was just like, oh, phew, we got one that we like.
Variational autoencoders, can they be mix and match with models, or do they have, you have to pair them with a particular model? That's VA1 with stable diffusion. You tried with Midjourney, it just would
Yeah, so the question is, do VAEs need to be paired with specific models? I'm not sure I'm equipped to give a great answer to that. What I'll say is you can ultimately build a VAE with anything that you want. Um, the variational part really comes from the fact that you are parameterizing some Q and you're using that to try to get your elbow up there. Whether you use a more complicated Q and whether you're doing CAD images or you choose to model, chemical properties of toxicity and solubility or whatever, like you can do anything that you want. But my understanding is that unfortunately the math gets very hairy as soon as you depart from the simplest distributions that have nice closed form properties. And but what we've said here, when we said there's a neural network, that neural network can be anything. You can choose any architecture, as complex, as deep, as wide, as whatever tricks you want inside that. That's just a generic function approximator. Okay. So that part of it, you have. And it's this business of exactly again, as we'll see next week, you can apparently, because I haven't read the chapter yet, you can think of diffusion as having this much more complex chain in terms of our priors than just the simple single Gaussian prior that we chose for this. This is really like the most simple case of variational inference. And like I said, there's whole books on variation. Yeah.
Okay. So kind of, in the examples that you saw, like clearly we began, whenever there's like some feature like, hair, right? It's completely unable to, it's very clear because, and that makes sense because it's penalized for it's has this compressed representation, like, oh, they have brown hair and they're looking this way and they have glasses, right? But it could never know, like, at this one spot the hair is shiny and at this one spot it's not, right? So to me that makes perfect sense that it's unable to do that. Like that it has to, because like it just generates like the average of like, what all the hair would be. This is like the the median of the hair color, right? So then to me, it makes a lot of sense that like either diffusion or hierarchical, like you predict, first of all, this is hair, and then within like you have something that then uses like, within the hierarchy, it can like predict like the structure of hair in this little sub element, like, oh, if this is, then the middle would be shiny and, the ends would be not shiny. And same with like diffusion, you predict like a blurry version of the hair and then you can fill in the details to that. Yeah.
Yeah.
Does that seem, yeah.
Yeah. So I apologize. I'm not going to be able to recreate the whole thing for the people online, but it has to do with like blurriness and so what happens is I talked about a very simple approach is you have a patch discriminator which encourages nice, sharp, realistic looking things. So it's emphasizing realism over accuracy. Like I said, I can't think of a good example, but if somehow you knew that there was some weird correlation that it had to be this way, oh, I'm sorry, that's not the way Bermuda grass grows. They had to have been pointing this way. It's not going to do that, right? So if you really like knew the gory details, but what you see now is along those lines. Yes, you can do this hierarchically, where you first say there is hair here, there is grass here, and so when you have I don't know all the latest models, but like DALL-E 2, for example, it would do a lower resolution image and then it would do super resolution. The super resolution was also a diffusion model, which meant that instead of just encouraging realism, it was at least smarter and it knew a certain amount of global correlations. And so then it could do a better job of authenticity in addition to high resolution. Whereas patch discriminator is just kind of a very simple poor man's fix. It's not a very smart fix, right? because it doesn't even know really, right? It's hair. It just looks at this tiny little
Yeah.
16 by 16 patch of pixels and says, does this look realistic? It doesn't even know if it's on your head or if it's in the middle of your nose. Like, why would there be a 16 by 16 patch of hair in the middle of your nose, right? It doesn't even know that.
Yeah.
Whereas when you do super resolution with a diffusion model, it has a little bit more global information and
But like
and so.
intuition for me is like the per pixel loss that we're doing with the VAE is encouraging it, it's discouraging it from confident predictions about like details.
Yeah, I'm not 100% sure, but I can tell you for sure any of the models that were originally built that used squared error pixel for pixel reconstruction loss always generated blurry images because they're sort of like, I'm just going to predict the mean for what this
Yeah.
pixel should be. And so if your hair has a range of intensity values, it's basically going to keep predicting towards the middle and you're just going to get blurry hair as opposed to no, even though that's the average, you should have distinct places where this hair strand makes this part darker and that part lighter. It just doesn't know that. And so that's where something like patch discriminator can help because it just injects that little bit of extra oomph, whatever. But it still doesn't tell you whether or not you should globally have hair in there or I mean some of the things that you can do in images, it's amazing that like you have things like reflections and highlights and they're in the right place, you know. So I haven't quite figured out how it learns that global correlations, but ultimately, yeah, that's pretty good intuition.
There is a dichotomy for spaces versus better performance, because my experience with biological models is that interpretability is much more important, at least for my collaborators that I work with, because they want to do an experiment that then says, okay, let's take that DNA sequence, let's take that sequence, remove it, do something to it, let's see if we still get the same performance, or we're really going to dissect the biology. But maybe the model is more performant without some of the constraints that you're describing. Can you comment on that?
So the question's about commenting about the trade-off between interpretability and performance. I'm not really an expert, you know, on everything, right? But I feel like interpretability is not generally directly sacrificed for performance. Okay. The main problem is it's just really hard to get your latent space to be interpretable in the first place. Okay. So there's two problems. The one problem is it's hard to encourage it because, like I said, the math is the math and it doesn't have to be aligned to our human preference bases. Okay. But the other aspect is it's entirely possible something is how do I say it? Like something is disentangled, but we're just not smart enough to realize it. Okay. So like if you're not an expert, you might not know that whenever the cat has slightly curly tips of their ears, that means that their tail also must have this other property, right? That could precisely be the way the genes are expressing themselves. And yet you could be sitting there and be like, darn it, I want the shape of my ears independent from my tail. It's just not doing it. So that's the other problem is that if you don't fully understand the domain, then you don't actually necessarily know how to interpret it. So I would say that, again, this is me being a little bit out on the skinny branches, but like if you're doing something and you're trying to build a model and you want it to do something, you know, and you don't yet yourself fully understand this space. Okay, like I feel like I'm pretty qualified to say like, okay, people's eye color is pretty independent of their nose shape, is pretty independent of their, you know, and so like I want those all to be independent. But like if I'm in some space where I don't yet really know, then do you even know whether or not they're disentangled or not? You might not. So I think that's the other layer is that when we're really pushing the boundaries, how do you even know? It's a problem right now that people are having in LLM interpretability research. So what you would really like is disentangled explanation of what's happening inside the LLM. But if what really is happening inside the LLM is, well, you take this thing and you average it with that, and hypothetically, you take the square root of that and then you do it over there, and that's how you know whether or not this is a noun. Like, you might be like, wow, this is really confusing and convoluted looking, and I wish I had a much more interpretable thing. It's like, no, 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 I told you exactly what the thing's doing. You just weren't smart enough to figure out that this is exactly the right interpretation for how to know whether or not it's a noun, you know? So I think that's a challenge that we have. So in LLM interpretability, you look for the ones that you can see. Like, okay, so this seems to be telling me that this is, but that's ultimately a challenge, is that, like, in interpretability, they're still doing like manual interpretations. And so it's like, oh, I found some of these are like very cool, very disentangled. It's very clear what's going on. And yet this other 600 set of features, I'm not saying they aren't. I just don't even know if they're interpretable or not, because I may not just be smart enough to know what they're doing. All right, just checking the chat. So that's not a question. And yeah, okay. All right, I think we'll stop things here. So thanks everybody for joining. Appreciate the questions. Always makes it more interesting. So hope to see you guys next week. Is our monthly ML papers. 2 weeks is chapter 18, diffusion models. And we don't know the location for in-person for either of those yet. Anybody who has a company that has an office space or knows of some space, please let Ryan or me know. In the meantime, we're just kind of hopping around, trying different locations, hoping to find something that seems like it would work as a regular every week place. All right. Bye, guys.